Good afternoon, everyone. How are we going this afternoon? Before we get going on anything today, I just wanted to say today is a strange occurrence for the lectures. It's not usual for the lecture to be on a Tuesday. It hasn't changed to Tuesdays. We just had a public holiday here in Sydney yesterday, so we weren't going to deliver the lecture on the public holiday, so we're having it here on the Tuesday afternoon instead of the Monday. And also, that means that today's lecture is not really a lecture as such. I mean, one could think of today's event as a live recording of a recorded lecture for people to watch later, because that's kind of how I'm treating this. I think this may have been the first one of these lectures that I haven't played a game or watched a movie before it, because a lot of the techniques I'm talking about today, I couldn't think of something that really exactly exemplifies those techniques in a sense. So I left it out for this one, and it's actually quite funny because I've recycled the thumbnail for this one because the thumbnail for this stream actually matched something that was in like the thumbnail from, it was the same as the thumbnail from the previous lecture, but I didn't actually make it up to the content that I'd written for that lecture, which we're going to be covering today. So yes, this is a surprise for everyone that I'm not playing a game at the start of each lecture. I probably would have done some film stuff. I actually have a film in mind for the lecture tomorrow, but I don't know if I can do that. Nearly everything that I've done at the start of the lectures, well, not nearly everything, but a significant portion of them have had small copyright issues. I haven't actually gone back to the recordings to see whether things have been blanked out, or whether it's still being shown and the copyright owners have said, "Oh, look, this is fair use. It doesn't really matter what he's doing with it." So we'll see how we go. Okay, so going over what we did last week, I can't believe that's actually quite funny just thinking about it, that we only hit 3D graphics last week. We did our transition from 2D to 3D. In my head, I feel like we've been in 3D for months. But obviously we haven't, because the course has barely been going for, it's been going for less than a month. But we looked at transferring what knowledge I've given you about 2D graphics to 3D, and then it turned out, strangely enough, from the way we were teaching it, that the majority of the techniques that I'd been teaching you for 2D graphics were entirely applicable for 3D graphics. And it kind of works that way because we decided to teach you that way. I mean, there's ways to do 2D graphics that aren't the way we were doing it with polygon rendering. But obviously, we were trying to teach you stuff that was eventually going to go into 3D. All we were doing was basically ignoring the Z-axis when we started out, but now we're going to start using it in a genuine way. And so we started to talk about 3D objects and how they're built reasonably similarly to the simple triangles and rectangles you've been using so far. But once the vertices kind of meet on the other side of an object, you create a surface for something, a surface mesh. We're going to go into more detail about how we work with those as we go along. I mean, really, we're kind of building up your capability in a lot of different like little bits and pieces as we go. So we go to 3D and we go, okay, what are the ramifications of going into 3D? What other things are we going to do? And a couple of those were the other things we also covered last week was cameras and using things like delta time for dynamic cameras and movement. Now, delta time is going to come up in lots of things actually, because it's not just movement of cameras. It's movement of all the other objects in the scene as well. And if you crossed over into just real-time programming, not necessarily graphics related, all of your stuff for control of objects, physics simulations, to a certain extent, the rudimentary AI that goes into computer games and stuff like that, all that's going to take delta time into account. So it's a fundamental concept that we don't technically need in a lot of graphics. A lot of our graphics is going to be we don't really care about what happened before and after. It's only what's happening in this frame, but it's still very, very important because anytime we move anything in graphics, it's going to take into account that delta time. And I think that's going to be quite important when we start thinking about the idea of animation and stuff like that. So over this week and next week, we're going to be delving into a side of graphics which is like we're bordering on the artistic side of things, like how we create things and how we move them and things like that. So we're going to be looking at like organizing complex objects and some of the ideas of how these things are created and animated and stuff. It's not necessarily going to be what you would be called on to do technically as a graphics programmer, which is kind of where we're focused in this course, but I feel like without the context of what a 3D artist, so like I've worked like this before where I'm there as the programmer, not just graphics programmer, but the programmer for an application, and sitting next to me on the next desk over is the artist who is modifying and rebuilding or building from scratch 3D assets. They've passed the 3D assets to me. We work together to put it into the scene and make it move around and stuff like that, right? So I think it's quite useful to have context for that, even if we're not necessarily going to be testing you and your capability to, say, create a Pixar character from scratch, right? We're never going to be like asking you to do that in this course. We may, for example, we may give you a character like that, and then you have to work on what is the tech to light this character, or how can we do some simple animations on this character. So we're going to teach you about some of that stuff. But I still kind of want to cover it in lectures. I'm going to at least cover it next week, a little bit of like how someone might take concept through to 3D model. Because even if we're not going to do it, I think it's useful knowledge to think about. All right, other things that we looked at was also model view projection transform. I mean, it really boils down to a single transform because we're not going to do multiple transforms when they're happening one after the other. We bundle them all up into a single transform. Particularly with those transforms, we looked at how to do perspective transform, which is one of the things that gets us the difference between a scene that looks two-dimensional, regardless if it is three-dimensional or not. It looks two-dimensional, but if we put it into perspective, things that are closer to you are bigger, things that are further away are smaller. That will give us the illusion of depth. It can get us to sort of trick our depth perception into not thinking that we're looking at a flat screen, because really we're looking at lights on a flat screen. There is no depth in our monitors, right? You can put your hand behind your monitor. There's nothing there that displays information. But we can trick ourselves into seeing it because a lot of our depth perception is based on relative movement of objects. Like, this is the funny thing. I like to talk about depth perception as two things, hardware and software. So the hardware for depth perception is the fact that we have two eyes, and our two eyes see things at different angles. They also see, like, you can kind of, depending based on what your right eye sees, your left eye can kind of see around things that your right eye sees, and by a tiny, tiny amount. The closer you are, the more this works. And so that's the hardware side, where that really only works up to about 3 to 5 meters away from us. And that gives us a stereoscopic vision, that capability to kind of tell how far away things are from us. The other part of depth perception is the software side, which is actually our brains interpreting the image. So it's very, very much easier to judge the depth of objects if you see an object you recognize. So in a distance, you see a car, for example, like you're looking down a street and you see a car. It makes it very, very much easier for you to tell how far away things are because it's a recognizable object. You get really funny things where people look at the moon and people say that the moon has changed size. And the funny thing about that is the moon does not change size. It's on a nearly circular orbit around the Earth. So the radius of the moon, the radius and diameter of the moon that we see is always the same. Yet, when it's closer to the horizon and we see it alongside trees and things like that, we think that the moon is bigger. And when it's up in the sky, we think it's further away, even though it's never changed size. And that's our wiring for depth perception, our software, our human software for depth perception, getting tricked by relative size of objects that are near each other. So the model view projection in perspective, the perspective projection gives us a little bit of a hint on those things because it replicates the size difference of things as they get further away from us in the real world. And so if we build a landscape or something like that in our scene that is realistic, and we have, you know, trees that are the same size, but our perspective transform makes some of the trees, you know, for you really big and other trees really small, we will see the difference in distance that way, even though it is technically a flat screen. And you can see this in, you know, in artworks dating from the Renaissance to the present day. People will draw something in the distance smaller than they will draw it closer to us, and we will see that depth even if it doesn't exist. So a lot of that stuff is really useful once we get into 3D. And so yes, that's the kind of knowledge that we're building up. So let's look at what we're covering today. The first thing that we're covering today is something that I was potentially going to try to squeeze into the last lecture, but I think it was a better idea to just leave it out and talk about it today. I am, but I'm still trying to squeeze 3 topics in one day. We'll see how we go with that. But the scene graph is a way of organizing objects, and we're going to leverage what we know about transform matrices, as well as just really simple hierarchical data structures like a tree, to do that. We're also going to look at depth testing, which is something that's, you know, I could get away with not teaching you this, but I didn't really want to. I wanted you to know the background of what's happening, because a lot of our OpenGL and our graphics cards just do this kind of stuff automatically for us. But I think even if it does it automatically, and this is seriously one line in code that you're going to implement, I didn't want to leave you without the knowledge of how it works and why the system works the way it does, which is what depth testing is. Blending is another thing that we're going to look at, and these two are actually very closely connected, which is why I wanted to do them together. Blending is about rendering transparency. So it's the idea that you could look through an object at another object. And if the object that you're looking through is not perfectly transparent, it has some color of its own, you would see color. Sorry, there was a question there. I just had to moderate. You would be able to see the color of one object and the color of the object behind it. Logan's asking, didn't we go through blending already in assignment 1? I don't know. Some people may have done some blending in assignment 1, but I don't think we had this kind of blending. I think we may have had multiple textures on one object, but this is like objects that are literally separate and in front or behind it. This doesn't make sense because I'm using my hands. Let me find something transparent. I've got this plastic box here, and you can see me through the plastic box. Separate, completely separate objects. One of them's see-through and the other isn't. Well, it doesn't matter whether the one behind is or isn't. But how do we render this? What colors should be on this polygon here based on the things that are behind it? I'll talk about that later in the lecture. Oh, right. So some people already were doing it because they were doing sprites and stuff like that. Yeah, totally. I'm going to talk about that. So I'm going to talk you through the theory of it, as well as some of the maths that goes into it. So, like, again, it's actually similar to the depth testing where you can just turn it on with like one line in OpenGL, but there's actually more subtlety to it. But let's get to it, and I'll show you how this stuff works. Okay, so the first thing I want to talk about is the scene graph. Let's get into some deep science. It's not super deep science, but anyway, relativity. There is no absolute position for any object in this universe. Not that we can tell. If we knew 100% where the center of the universe was, we could do things relative to the center of the universe. And that's assuming that there's only one universe, which we don't know for certain. When we get to like that level of physics, it just strays into philosophy. Like physics and philosophy get to come together because neither one knows what's going on. So you might as well make guesses and just see whether something maybe is logically true or not. So there's no absolute center or position of anything. So the best thing that we can do if we want to is relate things to other things. So that's all we can do. So for example, CSE, the computer science school is in the building called K17, which is the K17 grid reference in UNSW. The idea of K17 only makes sense on campus. Once you're outside of campus, it's like, what the hell is K17, right? What does that mean? But in UNSW, it means something. So we can say in UNSW, we're in this exact position. But then it's like, okay, where's UNSW then? Okay, well, UNSW is in this particular position on Anzac Parade in Kensington, New South Wales. And that is a specific position relative to New South Wales and Australia. Or not even Australia when you think about this. I looked this up. There's an Anzac Parade in Newcastle. There's an Anzac Parade in Canberra. There's an Anzac Parade, I think, even in Canada or something like that. So there are Anzac Parades. Oh, there's Anzac Parades in New Zealand as well. Obviously, if you know the meaning of Anzac is Australian New Zealand Army Corps. So they were also Anzacs. So there's Anzac Parades all over the place. So I can't just say Anzac Parade unless I say this is relative to Kensington, New South Wales. And if I say New South Wales, granted, I don't think there's another New South Wales in the world, but either way, we would have to say, yes, New South Wales is relative to Australia in some way, and Australia on our Earth is relative to the position of the Earth at the following latitude and longitude. I didn't know what these were. I had to look them up. And I don't know why they're so specific. This might be the geographical center of Australia based on the Earth. The Earth is the third planet orbiting the Sun, and the Sun is a particular star amongst the billions of stars in the sky in the Orion arm of the Milky Way galaxy. And it goes on and on and on, right? But it never gets to the point where you could say this thing is located exactly at a position. The best we can do is to say that I can tell where an object is relative to something which is a kind of a larger space that contains it. That's all I can say. But that larger space is in itself probably just an object that exists inside something else, you know. So that's all we're getting there. All we're getting is a relativity between objects, not necessarily an absolute. And so we're thinking like how this makes sense to us in graphics. This hierarchy of relative positioning is actually super useful to us because we can organize our graphic scenes in that same way. So what is a transform? What is a transformation matrix? It is just the relationship between two coordinate spaces. So all that a transform is going to do is say that I exist here in relationship to another space. So I can have my world space and I can have my object. And we've already seen this, right? I use a transform to put my object into my world in a particular position. That's exactly the same as me saying CSC is at this grid reference at UNSW. So it's in relation to a larger space. But we don't have to do this just at one level. We don't have to put every single object into the world. What we can do is we can have a hierarchy of objects. So we can have some objects that are made up of multiple smaller objects, and each one is relative to that object. So I've got an example here of something. So we build a 3D scene. And in this case, it's a simple rendering of a house in a scene. So our world, the basis of our scene, we might use the identity matrix for this because we want to keep things simple. This is the 111, the 3D loser, 111 on each of the axes, and it starts at 0, 0, 0. But that means each of the objects in this world are going to have a transform for where they exist. So we're not necessarily going to put the house at 0, 0, 0. It might be offset somewhere. It might have its own local coordinates in that, like, it was built in a certain system that had a very wide coordinate space, and so we shrink it down to put it in our world. Our house, our tree, and our road that have been modeled, maybe they were modeled by different artists. Someone's really good at trees, or we have an application that builds trees. We have those. You can just drag and drop trees of particular species, and like it will procedurally generate different trees that look slightly different from each other. So maybe we dropped in one of those, and there's no guarantee that had the same coordinate space as the house or the road, because these might have been made by people, you know. And so we drop these in, scale them to the right place, put them where we want them, and each one's going to be relative to the world. But what we can do now, and what is kind of cool, is that the house is not going to be made up of of a single object. You know, it's actually going to be made up of multiple individual pieces. that we're going to put together. And so this way I can say, okay, I'm going to build my house. And I'm going to have half a dozen people working on this house because it's a very, very complex piece of architecture. We need, say, a gameplay designer to look at the paths through the house, and we need different artists. So some artists are really good at decorations. So we're going to get them working on things like the curtains and the detail on the glass and stuff like that. Other people are really good at like realistic rendering of I don't know, weathered and damaged objects. So if it's an old house, we'll get them to work on the walls and the stains and then the floors and stuff like that. Whereas something like the curtains might be newer than the other parts of the house, right? So we'll get different people working on different things. So each one of them is working their own space. But when we piece the house together, we're going to say the walls exist in the house in a certain place, the window exists in the house in a certain place, and we can just put these objects relative to the house. We could have multiple windows, multiple walls, which means we could actually have copies of the same assets being put in multiple different positions. And so this graph here could get very, very complex, lots and lots of different objects, and that's fine. Because for each object, at each node in these, we will actually have a transform in each node saying the curtains relative to the window are just inside the window and hanging from the top of the window. So we have a transform that makes the curtains the right size and the right space to the window. And then we have a window transform to the house, which says the window, this particular window is on the north wall of the house, on the, you know, kind of right-hand side of the north wall. We've dragged it around till our translate and our rotate and everything are correct. Like we have applications where we can do that kind of thing, or you can do it manually, which is what we're going to do more in this course, because we're getting into the nitty-gritty of the coding. But you could place a window by doing a transform matrix and knowing where it is, right? And then that has its transform relative to the house. The house has its transform relative to the world. If I want to know where the curtains go, what I do is I can actually go up through this scene graph and multiply all of these matrices together, and I get exactly where the curtains are. So I can, based on these transforms in this hierarchical manner, know that the curtains are going to exist in a very specific place in the world, but the way we do it is it's related to the house and the window. And the cool thing about this, the thing that makes this really useful to us is like, okay, we're going through and we're testing our scene, and we realize, the house keeps leaving the shot. So as we did a camera pan, I'm going to teach you about those later as well. So we did a camera pan through our scene, and the house keeps getting cut off from the side of the frame. We're like, we really wanted to see more of the house. Let's move the house. And if all of these were separate objects, we'd move the house and the walls wouldn't come with it. So whichever pieces of the house were still attached would maybe move, but the walls and the window and stuff wouldn't. And so what we do is we break up our object by accident. But if we have this nice hierarchy of transforms, if I move the house, I don't need to change the transforms relative to the house, but if I want to find the exact position of the curtains and the house is moved, I would be going through and multiplying all of these transforms, which means the house moving takes its children with it and all of their children. So you get this beautiful hierarchical structure. Excuse me. You get this beautiful hierarchical structure where if we change the transform for anything, it will affect the transforms of everything beneath it without them having to change their transforms, because all of their transforms are just relative to the position of the house. But when we want their final position in the scene, we're gonna compose together all of the transforms that are the parents of this until we reach the root of the tree. So if we move the house, everything comes with it, and mathematically it just follows along. And that makes it really nice. So this hierarchical structure means that the more complex our objects get, they're still organized. So we don't have, like, if this was a flat structure and like the curtains and the window and stuff were in the world space, moving the house would be a very difficult proposition. I was like trying to find a way to describe that. It's like, it would just be, right? Like, you'd have to find all the bits and pieces in a scene that could have hundreds of elements in it, and you'd have to move them all the same amount. As opposed to saying, all right, I only move one object, and all of the pieces that are owned by it will then move. Usually, when we're working with trees like this, actually these are just transforms, and the only things that have geometry are the leaves. So these are just positions of things. Because, like, the window is broken up into, like, glass curtains and frame and other stuff like that. So the window doesn't even have any geometry itself. It's just the definition of the center point of this multi-part object, which is the window. So usually it's just the leaf nodes that have geometry, but that's not always the case. Sometimes we have geometry in the um, uh, non-leaf part in the other nodes of the tree, like the house here maybe. But often it's just like transforms, 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 and then stuff at the bottom. So the leaf nodes are the actual objects. And so we might ask, why are we using these? I think I've already said all of this. Classic. I'm going to read through this and make sure there's nothing here that I haven't actually already said. But yes, we can put all of our hierarchical matrices together into a single transform. We can also do interesting things where the house contains its local transform and it contains a transform relative to the world. The window contains its local transform, and then it multiplies its local transform by the house's world transform and says, this is my world transform. And then the curtains says, I have a local transform, and I see the window's world transform, so the window links one transform to the world, and the curtains can do a single multiplication. So if you maintain this hierarchy underneath the root of the tree. So each one of these has two transforms, one to the one above it and one to the very root of the tree. Then you can get away with only doing one matrix multiplication. You don't actually have to go through the tree to figure out exactly where you are. You can actually only relate to your parent and still be enough. The nice thing as well, as I said, it keeps objects that are made up of lots of other objects together. There's even really simple examples of this. Like if you just have a character, and I think this is very, very common in games for characters to have, in a sense, modifiable armor pieces. So you have the idea that, like, you've got your big shoulder pads or something, like, because people love big shoulder pads on armor pieces, and you get a new set of armor which changes the shoulder pads. You can take those shoulder pads off and put another set on, and then that way you've kind of put a piece into the hierarchy attached to the shoulder of the character, and then that is now a compound object, the character, and then that shoulder pad will follow the character around forever. So it's nice that you can just mix and match pieces like that. You can modify your scene graphs on the fly as things attach themselves to different objects and stuff like that. The other thing this allows us to do is we can have, separate pieces that can be used multiple times. So, for example, those windows. I mean, we don't always want to do this because in a game, people are going to notice if you use exactly the same assets more than once. But we could have one asset, which is like, it's got its own its own verts and textures and stuff like that, but we use it multiple times in a scene. We reuse that piece multiple times in a scene by just putting it into the hierarchy in different places instead of replicating it. I think the most common way that you'll see something like this used is, say, a patch of grass or a rock or something like that. If you do your rock in an interesting way, you can just rotate it in different ways. So you can have the front facing the player and then the back facing the player. And it's going to look like two different rocks, even though it's the same one. And your scene graph could allow you to just put multiple of the same object in the scene, just by saying there's one of this object here, there's one of this object here, there's one of this object here, in different parts of the scene graph. So it can do some really nice things like that. The other thing we do with this is we can do movement and animations and stuff like that using the scene graph. So one of the common ways to use a scene graph, I think this is my next slide. Let's see if it is. Yes. Finally got to the Final Fantasy reference. Let's say this character, Cloud here from Final Fantasy, is made up of separate objects. And you can kind of see, like, this is old school polygons right here. Like, a lot of these aren't even textured, they're just colored. I think the PlayStation 1, sorry, that this is on. I'm trying to remember if it even had texturing capability. Part of me is thinking it didn't, which is why these are all flat color polygons. We could have this made up of separate objects. I don't know if this model particularly is. It doesn't look like it. It looks like just one model. But I would assume that the sword is definitely a separate model. So maybe there's two things. But I'm just using this as an example for hierarchy. So I can have the character's position, and then the torso and the head of the character. And the head of the character might have some information, and the hair might be a completely different model that's attached. I mean, you can kind of see how complex the hair model is at this point. It's pretty funny. If this was a character that wasn't in a game where you could always see your character, or a game where you're in your character, or a third-person game, we might actually have a camera attached to the character. This character doesn't necessarily, but I wanted to put this in here to just show that objects attached to each other don't have to have geometry. Some of them could be objects that are just attached in the hierarchy to other objects in one way or another. We could have the torso, which is like usually something like the torso or the hips of the character is going to be kind of the center of the character that a lot of the other pieces are anchored on. And we have the right arm, right leg, left leg, and they're going to be attached to this torso in one way or another. And we have the sword, for example, at the moment attached to one or both of the arms. We don't usually anchor something to two objects at once, because then we don't know what the transform is. Is it this transform or that transform? So often if we're just animating things, it'll just be attached to one, but this one will be animating in a way that it doesn't move off that anchor point. One thing that we can do with something like this, which is interesting, is we can specify sets of transforms that are poses. So this is definitely a pose in the game. The character is in this pose, and the thing that makes this pose work is the transforms of the separate objects. There's more detail than that. I am going to talk about, not this week, but next week, I'm going to talk about animation and things like character animation and stuff like that. But we could have it if these were just like solid objects. We could say that these are all in specific transforms of the torso to make this pose. It is not the only pose the character can have. It can have other poses. A simple example is this sword is attached to the right arm. When the character's not in a fight, the sword might be attached to the torso instead, because it's like across their back instead of being held in their hands. And so we could reattach the sword somewhere else, and we could have sets of transforms and sets of linkages which are just like, okay, this pose is these transforms. This pose has the sword in another position and it's these transforms. So there's like a standing up straight versus this kind of combat on guard stance kind of thing. So what we can do is we could say there is a specific local transform at each node that makes it do a certain thing. And then the cool thing about that is we can say flick between these setups. So we're in this setup when we're on guard, this other setup we're just standing up straight, you know, and we can swap between these. So as I said there, we can move the sword from the hand to the torso and that kind of thing when it's sheathed. We can go even more beyond this if we want to. These different poses, if these poses are similar to each other, they don't even have to be that similar to each other. These poses can be running with your left leg forwards and running with your right leg forwards. And if we move between these poses, we probably need more than just left leg and right leg, right? But if we move between these poses, we can get believable animation. So we can get the idea that there's a position, then another position, then another position. And if we move between those positions like every, I don't know, I'm going to say once 1/24th of a second, that's a classic movie frame rate, basically, we would be able to believe that motion. So that's one way we can do animation. Or it doesn't have to be 1/24th of a second. We could be animating positions only once every quarter of a second. And in between those, we would be doing like an interpolation between those positions. Because we can actually take transforms and average two of them out, right? So we can take two transforms and average them, and we'll get one that's halfway in between the two. I'm going to talk more about that as well tomorrow. Oh, it is tomorrow, isn't it? I was about to say Wednesday, but Wednesday is tomorrow. Once I start lecturing, I just assume it's Monday. But yeah, so this is how we do a lot of things in animation of objects, which we would call keyframing animations. So we have those poses that are the key frames, the things that we've actually specified. And in between them, we can just get the computer to just deal with what's happening in between. So it's pretty cool like that. The other things that we can do is we could also say that certain transforms can only move in certain directions. I think one of the most awkward things we could do if we were saying like right leg, left leg or something is allow them 360 degrees of rotation, because then it's going to look really, really disturbing if the character's foot can just do a full 360 degree rotation, and the whole leg looks like it's just torquing itself out of its hip joint or something like that. So we could say, this thing will never rotate beyond these, outside of these particular orientations and stuff. The elbow would never go backwards and stuff if these arms are broken down into more pieces, in a sense. We can do these things to make sure that while we're posing our character and stuff, it remains within, I don't know how I'd call it, like a set of rules. A set of rules that we've decided are the way we want to do things. So if the character is modeling a human, then we can make sure that it doesn't leave the general kind of parameters of human joints, like my elbow here. If that starts going backwards, can be a little bit freaky. So yeah, these are the kinds of things that we might use a scene graph for. We could use it for stuff like scenery, and we definitely will use it for complex scenery. When we're using it for a character, we'd have this character also having its own local transform in the world somewhere, but it might have all of its details here. So in this kind of zoomed in scope, for a character, we would use it for organizing pose positioning, as well as what objects are attached to the character at any particular point in time, and things like that. Whereas here we might use it for just placing objects in a scene and being able to organize those objects into kind of sub-objects, compound objects, and things like that. So if I want to move the house, I move the whole house and all its stuff comes with it. If I want to move the window within the house, I just move the window, but its glass and curtains come with it wherever it goes. So it's nice. I like these because they are going to give us a really clear and human understandable way of organizing everything, so that objects are kind of contained in other objects. And so if I pick up the house, I expect all of its stuff to go with it as it moves around in our scene. And this is the mathematical way that works. So the way that we might code these kinds of things, generally, our scene graphs are implemented before we get to OpenGL. So the way that we organize our objects and things is not something we're going to put on the graphics card. This is where we think carefully about what gets delegated to the graphics card and what gets done on the CPU. So we could think about it like the GPU is there to help us decide what colors to display. Right, so we can think about that, like that is helping us decide what the visuals are, exactly what the visuals are, but not necessarily the composition of the scene, not necessarily how the scene gets put together or how it's moving and things like that. So that's why things like our delta time, our camera controls, our position of our objects and stuff like that is handled by our CPU, because the CPU might be doing all of the thinking side of things and the GPU will be doing the purely visuals side of things. So if we draw that line, and it's not an exact line, you know, sometimes there will be crossover between the two, but it's useful to think of them that way, in that we have two different processors working at the same time. This is something reasonably unique to graphics, is that the two processors, which to a certain sense are both kind of capable of doing the other one's job, just not as well. So us separating the tasks between them is a choice of which one's better suited to what. So what we're likely to do with things like scene graphs is we're going to build those ourselves in our code. So what we're going to do is build a tree, and I'm assuming that everyone's familiar with trees at the moment. If I told you to code this structure, people would instantly be going, okay, cool, we can do this. We'd use a struct or a class here, depending on what language you're working in. And then each one of these would have pointers or references to the things below them, and then also have pointers or references to the parent above them. We might constrain this quite carefully so that every object only has one parent, because if it has multiple parents, then we can't compose a transform safely because we don't know which one it's going to be. But if it only has one parent and every parent can have multiple children, then we can always go up the chain to build a single matrix for each object, because that's the key, right? In the end, every object must have a position in the scene. So we need a way to have a one transform. So we can do this, like we can have a tree. Someone said it's been so long since they've seen a tree. Yeah, Jason's saying, so a lot of things moving around is probably CPU bound, unless you use GPU directly for something like particle physics. Yeah, I haven't really talked about particles. I will see if I get time. I'm not going to, I know. I've got my plan for the course, and as you can probably tell if you're watching the course outline really, really closely, as I've delivered the lectures, stuff has sort of shifted around there, but we're still on the same plan for the course. And as much as I'd like to teach you about particle systems, they're a stretch goal in a sense. Like, they're not the core of your understanding, but either way, we can do stuff like particles and like flocking algorithms and stuff like that. Simulations of stuff like fire or explosions and stuff like that. A lot of that can get really messy and can happen either on the GPU or the CPU. But a lot of the time when we're just moving objects around, so for example, we're doing a city scene and there's lots of people walking around the streets, and then there's cars driving on the road, and there's like birds in the trees and all this kind of stuff happening. The majority of that is going to be done by the CPU. So what we're going to get is this node structure, which has everything. The scene graph is going to be managed on the CPU, and then what we're going to do is pass the objects to the GPU after we've figured out where they are in the scene graph. So each node in the scene graph contains a local transform. If you just go up the tree, you'll find out exactly where something should be in the scene. Once you know where something is relative to the scene, you throw that into the vertex shader, and then it will do all its work from there on, because the only thing that the vertex shader kind of needs to begin doing its work is to know where something is. But it doesn't necessarily want to know just the local transform relative to the object above it. It needs the local transform relative to the world, so it can do the local to world transform and then pass everything through to the camera view and things like that. So yeah, so it's a really, really nice way of working with things, and it's a really nice way for us to organize our scenes so that we can use them. But yes, the code for this is more likely to be like a pretty simple kind of thing. Like you have a struct with some pointers going up and down, right? Pointer to your parent, multiple pointers to your children, or references, depending on what your language is. Okay, so those are scene graphs. I'm going to move on to depth testing. Depth testing is an interesting one, because in the real world, we don't care about depth testing. In the real world, depth testing is blindingly obvious to us, and we don't need to think about it even in the slightest. I was going to put a photo on this slide or something, and I was like, well, what am I going to put? If you try to look through an object, you cannot look through it. It's that simple. This is something that by about, I don't know, humans at age 1, I don't know. Don't quote me on you know, children's development or anything like that. But at a very, very young age, we come to the realization that you cannot see through things to see other things. This is really, really simple. We know this. Light does not pass through most objects. We're not going to worry too much about transparent objects just yet. That's actually later in the lecture. In the second half of the lecture, we're going to talk about transparent objects. But light doesn't pass through most objects. So the only objects we can see are the ones closer to us. So I can see this hand, and if I put this hand up here, you can see it, but I can't see it because it's blocked by this other hand. It's pretty simple stuff. So the object that we see is the object that's closest to us, and anything that's directly behind it, the light can't pass through because the light moves in straight lines most of the time. Let's not talk too much about moving through different density objects and things where occasionally, very occasionally, we're going to get to that level of simulation of things, like when you get thinking like explosions that do a shockwave that ripples out, like the Matrix style thing, and stuff that warps the scene that you're in. We can do that for effect in computer games, definitely. But we're not thinking about that right now. We're just thinking about the simple thing of, let's see the object that's closest to us, and we can't see the objects that it is obscuring. So in polygon rendering, if we go through all of the maths that we've done on polygon rendering, all of our capability, and we go, how do we tell which things we can see and which things we can't see? There is nothing in the maths that helps us there. I mean, there's stuff that helps us, but there's nothing that does it. Because in polygon rendering, there is no notion of light moving. There's no notion of a beam of light from a polygon into the camera. Like, there is no notion of a straight line of light coming from that to the camera. The only thing that we've done in order to get the idea that we're looking at things is to mathematically shift stuff around and warp it so that things are the right size if they're closer or further away, and things are in the right position from the camera's viewpoint. But this doesn't in any way give us the capability to say there's two triangles and there's one in front of the other. Let's do it in a way that you can see everything that I'm saying. So I can have my two hands here, and in polygon rendering, it has no idea which of these two is going to be in front of the other, unless we do some complex mathematics to actually, say, draw a vector from the camera through them both and say, okay, different lengths of the vectors at different positions. So we could do that if we want to, but that could get very expensive. So all we've done so far is mathematically project objects into a view space, but we can't really tell if something is obscuring something else. So we need to do something more. We need another process on top of this. Again, this is something that's actually been turned on by default, but I want to show you how this process works. So what are our options? Our options for rendering depth. There's one option that I offer. You always know that I'm going to do this, right? If I offer you an option and I say I'm offering you an option, it's going to be wrong, and then I'm going to show you why later. But let's think about a simple way of doing this. If we ordered our triangles from the back of the scene to the front of the scene, and we render them in that order, then it's totally going to work. Because what we're getting is the idea that, you know, when we had a single triangle and we were talking about the OpenGL pipeline, that triangle would get rasterized, so it would choose which pixels it was appearing in, and then each of those pixels would have a fragment, and that fragment would be rendered into the pixel color. So that's how we go through the vertex shader, the rasterizer, and the fragment shader. If we have multiple triangles that want to appear on the same pixel, each of it's going to have its own fragment. And so two fragments are going to try to write to the same pixel. We need to deal with that conflict, and one easy way to deal with that conflict is say, if you're at the back, you render first. And then if you're at the front, you render afterwards, which means any of the pixels, any of the fragments here that were in the same position as the fragments on this one will just simply overwrite the fragments from this one. So what we get is, if it's closer to you, it gets rendered later, which means it overwrites everything in the background. So it's kind of like you paint a picture and you paint the horizon and the sky or something, and then in front of that, you paint the mountains in the distance. This is totally Bob Ross, right? Bob Ross technique. You paint the mountains in the distance. And then after that, you paint the trees that are in front of the mountains. And so every time you paint another layer of this, it covers up the layer that was there before. So even though we did render the entire background and the entire polygon that's behind, it doesn't matter because we're going to override it. And the one in front is going to kind of take precedence because it's closer to us. So that feels simple, it feels clean. Yes, we're going to be redoing some work depending on the number of triangles we have. Like, we might be writing to the same pixel several times with multiple different fragments to the same pixel, but we're still going to get a nice clean output. where the thing that's at the front gets rendered last, so we see that thing clearly. But the question I have here is, are we going to like waste a lot of time sorting our triangles? So I was going to do a full time complexity analysis of this, but I didn't go that deep. But either way, if we're going to sort the triangles in a scene, we're probably going to have some kind of n log n algorithm to sort. It's like we're talking about like quick sort or merge sort or stuff like that. So I'm not gonna go back over sorting algorithms. I'm pretty sure people have learnt a little bit about sorting algorithms. But what we're talking about is Sam saying use BOGO sort for the order 1 potential. Actually, what I would probably do in this situation is a what's it called? Hash sort, map sort, where you go for order 1 insertion into a buckets sorted list. It's not bucket sort. Wait, it is bucket sort. Is it? I can't remember. It's the one where you use a hash table and just drop them in based on their depth. Because the order n log n thing involves a very precise sorting and moving things around so that they're reordered. We could do that. Either way, we're probably going to be n log n, or if not, we're in order 1 or order n, maybe, if we're lucky. Order n, but not super accurate about it. Sam's saying, yeah, I think it's bucket sort. Yeah, I think it's bucket sort. But anyway, what we're getting is somewhere in the realm of, say I've got 100,000 visible triangles, 3 verts per triangle. This is like your average AAA game is going to have probably more than 100,000 visible triangles in a single frame. So if we need to check all the 3 verts, we've got 300,000 n log n. It's going to be somewhere around 500,000 memory accesses. So that's like 500,000 memory accesses. That's not that big a deal because our memory is like going at something like 3 billion accesses a second. The only problem is that those memory accesses are not going to be local to each other because they're going to be verts, and our index buffer points into our vertex buffer in strange places because you can't necessarily guarantee that all the verts are going to be next to each other. So we're talking 500-ish thousand. I'm ballparking all these numbers. Please don't quote me on them, right? Separate memory accesses all over the place. We would have to rewrite and reorder the index buffer so that the triangles are then in a specific order. Then we'd pass those triangles to the vertex shader. This may feel time consuming to you because it is. We could nearly consider this to be a very big waste of time because we're getting to the point where, oh yeah, sorry, when I said our memory is capable of 3 billion accesses a second, I want this thing to happen 144 times a second. So that 3 billion then drops down a lot. And those 500,000 memory accesses start to become a significant percentage of the time that we're rendering each frame. So this is already starting to look like something that is not feasible for real-time programming because we haven't even done any rendering. If we have to do all of this sorting before the rendering, Jason's adding things up there. Hexus once said, don't quote me on this. How many times have I said that today? I mean, like, this is what happens when I do hand-wavy maths. What I'm trying to convince you of is that if we multiply all these numbers together and things, we're going to get a significant, a measurable percentage of our frame calculation time is going to be spent just ordering things. So we've missed out on all the cool stuff that we might be doing in our fragment shader. So the fragment shader is where we're going to do most of the work when we're working on graphics, and that's cool lighting effects. Cool lighting effects, reflectivity, even just like nice effects like cleaning up our pixelation of things, accessing different textures and things like that. All of that cool stuff is going to happen in the frag shader, but we're taking up all our time before we even get to the vert shader in reordering things and then having to send a new index buffer across the bus to the graphics card, right? So this is super, super messy. All I want to say to you is that this feels like it's going to take too much time. So that's one reason why I think maybe we shouldn't be sorting these triangles. Maybe we need another solution. But there's a bigger problem than that. There's an even bigger problem. I'm trying to sort triangles, right? Triangle has 3 z coordinates, so we can have something simple, right? So if the z coordinate in our world space is aiming towards our camera, so this is view space by this point, aiming towards our camera, triangle has 3 z coordinates. Let's give you an example here. I'm just making up these z coordinates here in this diagram. Which of these triangles is in front of the other triangle? Z equals 3, z equals 4, z equals 2, z equals 1. This side of the triangle is super obvious, really simple. These 2 points are in front of these 2 points. So if we compare only this side of the triangle, the aqua, teal, aqua? Yeah. I love it's like aqua, teal, turquoise. It's like, what color is that? They're all the same. They're not all the same, but they're like, you know, anyway. So this side's in front of this side, yeah, but over here, but we've got z equals 2 and z equals 6. Which means on this side of the triangle, this point's in front of this point, which means these 2 triangles are clipping through each other at some point in the triangle. And do we want to do all the complicated geometry to figure out exactly where they're clipping through each other? I love it. Someone says, I vote turquoise. All right, it's going to be turquoise. I'm going to call this turquoise from now on. So at some point, the turquoise triangle pierces through the center of the orange triangle and comes out the back, but we don't know where. And this can happen when objects pass through each other. So for example, a character walks through, is walking through like a forest, and they pass through the leaves of a tree, and we're like, look, let's not do a whole physics simulation for how the leaves are going to work. I mean, we'll do that in the demos when we're trying to sell stuff. But either way, we're going to clip through these things at some point. How do we tell which of the 2 of these is in front? And there's no way to do it, because there literally is not one of these triangles that's in front. So my whole thing here about going, okay, let's go through to all of this trouble to order these triangles, that might not always work. You're going to have triangles that literally aren't in front of each other. And what do? Are we going to like add a vertex here and here where this triangle cuts through the other triangle, and then split this thing up into a quad and a triangle, and then split this thing up into 2 triangles that are in front of this, and then after we've split it up, we resort the entire scene? It's like, no. It's already too expensive. So not only is sorting all the triangles too expensive, sorting all the triangles is also technically impossible. So that's awkward, isn't it? I like doing this where I go, okay, here's an idea, and now I'm going to tear it to pieces. That is how one should work with ideas in general. You have an idea for something, you don't know it's going to work until you have tried to tear it to pieces, and then afterwards you go, oh, okay. This is how we find a different idea. Granted, this kind of stuff is obviously me stepping through, you know, I don't know how many years of graphics research. There's probably like 20 years of graphics research with moving through these possibilities. Because if you do look at the way graphics was done, let me say 30 years ago, I want to say. What is 30 years ago puts us around 1990. 25 years ago, so when we were talking about Quake and stuff like that, you can look up this thing called BSP trees, where literally all the objects in the scene, all the triangles, are put into a tree, and the tree is a depth tree. We don't even do that anymore because it's this, and it's slow, and so we don't do it. So there were actually techniques we're using to try to turn this into a binary, you know, because it's like computer scientists. It's like, we've got a problem that has massive time complexity. What are we going to do? Oh, we'll throw in a binary tree that'll halve it. It's like, yeah, okay, fine. We always do that, right? And that's not a bad way to start every attempt to solve an algorithm. But in graphics, we didn't solve it that way because we just went, these triangles aren't necessarily going to be in front or behind each other. If the triangles are not going to be in front or behind each other, then let's go to a step further. Let's go to a more fine-grained way of looking at these things. So if we can't depth sort triangles, why don't we depth sort fragments instead? So if we have triangles, or parts of triangles, better yet, parts of triangles, not triangles, that are in front of each other, then why don't we just do this on a per pixel basis? So per pixel basis means that we're looking into our view frustum through a pixel, and if we trace that line into our scene, we're going to see multiple triangles. All right, we're going to see a background somewhere. We're going to see say a house and then a person standing in front of the house. We go, which one of those things is the one that's going to be rendered? So the rasterizer for each of those triangles is going to go through each of those triangles and create a fragment for each one of those. That means, as I said before, we're going to get more than one fragment per pixel. So what we get is, for a pixel on our screen, if we have more than one fragment based on the triangles that pixel could see, it's not seeing, but we need to decide which of those is going to be the pixel that's actually visible. Okay, so I set up the problem there and I've timed it perfectly. So we're going to go to break time, and after break time, I will then show you how this works. So I'm basically baiting you into continuing watching this. As Sam is saying there, teaching is just like advertising. I consider teaching to be a bit of a performance, I spend a lot of time in theater, so teaching and performing kind of, it follows. It's the same kind of thing. You want to take people along on your story and your journey. So cliffhanger, and it's not an ad, it's a break time slide, which is cooler than an ad. I'm going to, there's nowhere to put, wait, I'll put myself down in this corner. I made this slide really busy, but there's all this stuff I wanted to talk about because like, we're starting to have the majority of the tools that we need to build graphics, and I wanted to look at the different ways that we can use the technology, because there isn't one way to use the technology. Every piece of technology is there to help in some way or the other, because the graphics card can be used to do very, very realistic things, or it can be used to do very, very stylistic things. And so I wanted to look at art styles and how they're used in films and games. So I have two films here. Well, I have an entire family of films here versus a single film. But then the Lego Movie could be considered a family of films because there's several of them following from the original. The Lego Movie, which is quite funny because like you'd consider the Lego Movie to be a completely fantasy movie, but it's set entirely in the real world, which is a very, very interesting and strange thing for an animated film, but it came off so well. Look, even in this photo, you see, well, what are we seeing? We're seeing reflections of plastic surfaces. You can actually see a mold line coming down the middle of his hair there. So what they did was they took these objects as if they are small-scale manufactured objects, and they kept all those things in it. There's manufacturing defects and stuff like that in each and every one of these characters. So what we get is this thing looks like it is a stop-motion film up close with a macro lens camera on these things, and they have really exaggerated depth of field for that reason as well. And all this kind of stuff. So the entire art style, even though it's a movie that is like impossibly unreal, it's set in the real world. So this is hyper realism. There are like tiny little surface scratches. There's actually like, even like, it's hard. You have to look through really closely frame by frame. There are fingerprint scuffs on the Lego characters and stuff. So you can actually see that these are like Lego that's been played with. So there's this beauty in that kind of realism. They also removed all motion blur from the film to make it look like it was stop motion. So even then, trying to get it to look like it's stuck in a real world. Whereas you take the majority of the Pixar films, which is a fantastical world, has exaggerated proportions, strange physics. I mean, look, the Lego Movie did not have real physics either. But even then, when stuff falls and stuff in the Lego Movie, it falls like a small, like 5 to 10 gram object. It doesn't fall the way a person would fall. It falls and bounces in funny ways, right? So it's really interesting stuff like that. Whereas the Pixar films are much more of this fantastical kind of thing. It's funny, I was trying to think of like movies for realism, and I was like, I need a movie that's entirely CG that does realism. It's actually very hard to find one. Other than saying movies that are entirely real but have heaps of CG in them that you didn't realize. I'm thinking of movies where they've replaced so much stuff with CG, but you just believe it, and it's set in the real world. One I can think of is Great Gatsby. All the Jurassic Parks and stuff is meant to be set in the real world. So all of the details are mimicking realism. Those things could work. But yeah, the Disney Pixar films, no attempt at I mean, there is to a certain extent. Frozen has some really, really amazing snow simulation, by the way. Anyway, I don't want to get too fast. This is the break slide. In games, we get the same kind of thing happening. So I took two games here that particularly try to get to realism versus stylized um, uh, graphics, but these are obviously just examples. But I did pick two games that are arguably the biggest kind of games of them, because Red Dead Redemption 2 is one of the biggest selling games of all time. Genshin Impact has not necessarily released their numbers, but I guarantee has made more money than any other game in 2021, I'd say. Just because I'm watching people put hundreds of dollars into this game and I know how popular it is. If you look at the difference of the art style, it's very, very interesting, where this is doing its absolute best to look like a photograph of a real kind of area in the United States Midwest kind of thing. I don't know where it's set because I haven't played it yet. The proportions, the horse, the foliage and stuff like that is trying to be real world as it can be. Whereas Genshin Impact here, it's no less technically difficult to do something like Genshin Impact, because what Genshin Impact is trying to do is create a world with its own consistency within it. So the entire world of Genshin Impact must look like it's an anime. And so you can actually see the different levels of success here, but the lighting is so oversaturated to be this beautiful kind of, I found this picture at sunset, so this is my actual game here. But the character here is done in a kind of cel-shaded lighting style. The only thing that breaks it for me here is that the platform that she's standing on, I picked this, right, is done in a semi-realistic style. So there's one little thing that doesn't quite come off here. But either way, no one's going to mistake this for the real world. Whereas here, you could, if I said this was a photo, then people would be like, that could be a photo, right? And so you get this kind of thing where we can use our graphics technology to either push to get people to believe that things are real versus take people into a fantastical world, which still has to be believed. But we believe it follows its own rules. We don't have to believe it's the real world. So we take, I use Genshin Impact. We could take nearly everything that Nintendo does for this, and we believe Nintendo a lot because it's beautiful, right? It doesn't need to be realistic to be beautiful. And so you get these two different arms of development, I guess, in things where we're using the graphics tech to do really cool things to trick people into believing things. And either way, you can trick people into believing something's real, or you can trick people into believing that they are in like an anime or something like that. Okay, let's take a break. It's 5:08 by my clock. We will come back at 5:13, sorry, and we'll continue what we're talking about with depth testing, and we'll talk about blending after that. Okay, back soon. Hello, I'm back. Pretty funny talking in chat at the moment. Let's do let's take a official university lecture and turn it into a Genshin Impact strategy discussion. Okay, as I said before, I said that we were going to do some depth sorting at the fragment level rather than at the triangle level, and I said, let's do this after the break. It is now after the break. So where we're up to now is the depth buffer, also known as the Z buffer, Z buffer, depending on where you're from. Someone's like, I don't see the problem if we're studying Genshin Impact. If I was going to do a course on game design, something like Genshin Impact would definitely be part of that. We would be looking at the interesting issues of aggressive monetization in games, because I think Genshin Impact is a very good example. I think what we would do is we would take Genshin Impact and Star Wars Battlefront 2, and we put those next to each other as aggressive monetization of microtransactions in games and study them both, because Star Wars Battlefront 2 got a massive backlash, had to wind it all back and kind of stopped doing it. Genshin Impact has been successful at raking in millions of dollars. Somehow still works. Don't know why. Massive backlash for random things in Genshin Impact, but it doesn't change their bottom line at all. But anyway, let's not get into that. Okay, so I said we were going to talk about if we're going to do depth sorting at the fragment level instead of depth sorting at the triangle level. How would we do that? So what we do that is this thing called the Z buffer. It's like the frame buffer. So the frame buffer is the size of your screen or the size of the window that you're intending to display, and for each pixel, it stores color information. The Z buffer doesn't store color information. Instead, it stores depth information. So here's something that a Wikipedia user put together, but it's just such a perfect example of this. It was really easy for me to use this. You can see that the Z buffer is a single dimensional buffer. So it goes from white to black, or it goes from 0 to 1. You can 0 to 1 can be white to black if you're going to render it as something visible. So here, off in the distance is a lower number, and closer to us is a higher number, and the higher the number is, the closer it gets to black. And you see that the objects themselves are darker than the background behind them. Objects here also darker than the background behind it. And then the kind of plane that we're looking down on gets brighter as it gets closer to us. So every time we someone noticed the monkey. This is one of the you know, like the teapot. This is another one of those objects that gets used a lot in computer graphics. This is another reason why I had to put this slide in. Every time a fragment gets rasterized and gets put through the fragment shader, in the fragment shader, we can tell what depth the fragment is. Because in the same way we're interpolating the position or the information from vertices and stuff like that in the fragment shader, we can tell exactly what the Z depth is of this. And so what we can do is we can take the Z depth and we can basically, it's not exact, but we can basically store the Z depth of the object in this buffer. And then what we'll do is when we've rendered that fragment, we put its color information in the color buffer and we put its depth information in the depth buffer. So we have two buffers that are effectively the same size in terms of the number of pixels. They're not in bit depths, they're slightly different. But the bit depth of the Z buffer is usually about 24 bits. So 3 8-bit things into a single float. But you can do 16 or 32. Different implementations use different Z depths. But either way, it's a single number that tells us between 0 and 1 how close to the camera things are. The trick then is, if two fragments are trying to render into the same pixel, they will check the Z buffer when they render. So multiple fragments are trying to apply a color to a pixel. They do not know who's in front and who's behind. They also do not have any guarantee that the one behind renders before the one in front. It could happen in any order. So whichever one happens, the first fragment will always store its color and depth information in the buffers. Any subsequent fragments that try to apply to that same pixel will test their depth information against the Z buffer. So the first thing they'll do before they go into the complicated stuff about colors is they will go, what is my Z depth from the camera? And it'll be like, am I closer to the camera than the current thing in the Z buffer? If I'm closer to the camera than the current thing in the Z buffer, then I will replace its color with my color in the frame buffer, and I will replace its depth with my depth in the Z buffer. So in this example here, if we had a situation where the background plane was rendered first, all of these areas here would have been colored gray, and they would have been colored this nice even gradient in the Z buffer. But then when we go to render monkey here, we would have this section here and be like, ooh, this is, if we test against the Z depth, this part of the monkey is in front of the Z depth of what is in the Z buffer, so it's going to replace it. So these colors replace the gray that's in the background. We could go in the opposite order as well, where the monkey gets rendered first and then the background plane got rendered later. When we reach these fragments here, we do the Z depth test and we say, oh, I'm behind what's currently in the Z buffer. So if I'm behind what's currently in the Z buffer, I will be discarded. So the color from that background plane, when it reaches these fragments and it hits this part of the Z buffer and it says, oh no, I'm behind this, I should not render, so it will not replace the color. So it's a pretty simple thing there where you just go, we're still just going to render everything. But what we're going to do is per fragment, we're going to see whether we're in front or behind what's currently rendered for that pixel in the scene. So it's actually a pretty simple process because you're still rendering everything in the scene. So there's that cost. But the cost of trying to remove things from the scene that aren't visible is kind of too high to try going through, because then we incur this kind of like massive cost of sorting everything where it wasn't always necessary. So what we can do instead is we just render everything. So we don't have to do the sorting in advance. We just jump straight into our shaders and we go in and we don't check depth until the fragment shader. And the fragment shader says, I built a fragment at this depth, and then I try to build another fragment, render from the fragment to the pixel for the same pixel. All I need to do is test whether I'm the thing in front. If I'm the thing in front, I render. If I'm not the thing in front, I don't render. So it's actually quite a simple process, but it is not without its issues. So Z fighting is one issue. No, this is not a Dragon Ball reference. I should have changed this image to like a picture of Goku or something like that. Anyway, that's a bit of an obscure reference. But anyway, the Z buffer doesn't necessarily have perfect precision. We can't always tell exactly that two objects are definitely closer than each other. Sometimes we can, sometimes, we only have a certain number of bits. Right, so if we have 24 bits, which I think is the default for the Z buffer, we can most of the time tell objects apart, but sometimes we get this thing called Z fighting. And what it is where fragments are so close to each other in their Z depths, they're fighting over which one's closest, and you'll actually get flickering between these objects, and it's super obvious and super annoying. The kind of situations where this might happen is when you have a building placed on the ground, and the building's been placed on the ground in such a way that the floor of the building and the ground texture are too close to each other, so that when you look down, they actually sometimes flicker in real time. You won't see this nowadays. I think this is something that happened in the 90s or so, but we have much better kind of techniques to deal with this. Yeah, Jason's saying, I was going to say this as well, that it's not necessarily going to happen in the fragment shader, because the fragment shader is actually a very, very busy part of the graphics process. A lot of the time with depth testing, we'll actually be able to do that before the fragment shader is invoked, and we can discard fragments before they get to the fragment shader. And Hexus is saying, is this to do with float arithmetic? Yes, this is definitely to do with both float arithmetic and float precision. So if we've got a 24-bit float, if you've ever played around with the difference between a 64-bit float and a 32-bit float, for example, like a float and a double, you would have seen the massive differences that can come out between those things because of the level of precision difference. This is an artifact of that, and it's called Z fighting, and it'll be two textures kind of flickering through. Zaya says this still happens in games like Arma 3, so yeah, you can totally get this. So the question is, how do we fix this? There's two approaches to fixing this. One is at an art level. So at an art level, we can be careful how close we place objects to each other. We can be really careful with our scene so that objects are not placed really on top of each other. In a dynamic environment, though, how can we control this? We can't necessarily control this if things are going to be moving around. There's going to be like destructible terrain, all this kind of stuff. Like we don't have that much control. So the other thing we can do is at a Z buffer level, and this is the way the Z buffers actually work, is that the Z depth is not literal. It's not a literal Z depth of how far away things are. What we do is we use a different part of the Z buffer space depending on how far away it is. So the closer something is to us, the more of the 0 to 1 range we use. So for example, I have a 100-meter depth scene. The back half of my Z buffer might cover 80 meters of that. The front half of my Z buffer might cover 20 meters of that. And then the front quarter of my Z buffer might actually cover as little as like 1 meter or something like that. So the closer something is to you and the more likely it is for you to detect the Z fighting, the more precision there is in the Z buffer and the less likelihood that you're actually going to get Z fighting. So the Z buffer is not actually just a linear distance from near to far. It might be a great deal of the Z buffer is used for the first sort of 3 meters of vision. And then like the final 100 meters of vision is just going to be like a very small amount of precision, because all you need to know is like, is that entire tree in front of that building? And is someone even going to be able to see that? And if they aren't, we don't need to be that careful with the depth. So something really far away could clip through each other and you're like, oh, whatever, you know. But if the cabinet that someone's opening right in front of them starts Z fighting with its own shelves, then we've got a problem. It's going to be really obvious. So a couple of ways that we get around this. We've never actually kind of completely solved the problem. It's not really something that can be solved, but we can get around it. Yeah, Hamish is saying you can still get this if you try to get it. Simply setting two things in Unity Unreal to have the same Z will do it. But you can add 0.0001 to one of them to space them apart. So that's the art level solution, is just space these things apart a little bit and you'll probably get away with it. So in OpenGL, in the actual code of how we do this, we don't actually have to do much code for this. So we don't have to implement a depth buffer. In the same way we don't implement the frame buffer. Either one of those things wouldn't be that hard to do. All we would do is tell our graphics card, please make a buffer of this size, which I think you do when you're opening a window anyway. But the depth buffer is usually on by default, and OpenGL is already doing these things. So if you've started so far, although I think tutorials last week, you were actually already using a depth buffer without knowing it, because OpenGL is just going to do it if you put objects in front or behind each other. But if you want to, you can actually enable specific OpenGL depth testing. And you can play around with it, write custom depth code and things like that, which means that you can actually screw with the depth testing. You can get it, instead of depth testing to have objects in front of each other, you can have the behind objects render and the front objects not render if a behind object is obscuring it. Way to screw around with your brain's expectations for perspective and vision if you do that. It's actually really interesting moving around in a scene like that, because it's very, very confusing, because what your brain's telling you about depth for the parallax motion of objects is the opposite of what it's telling you about objects obscuring each other. So it can do funny things to you. Don't break your brains, by the way. You can break your computers, you can replace them. Brains are different. Okay, so that's depth testing, but I'm going to move on to another thing which involves depth testing in a certain way, but is also a little bit different, but super interesting, because it's another kind of concept where we're trying to replicate something that happens in the real world, but the ramifications of us working in this polygon rendering world force us to do things in a very strange way. So blending is how we do transparency in OpenGL. So this is blending colors from different fragments together. So two different fragments that are trying to work on the same pixel. So before we said whichever one's in front, it renders, and the ones at the back just get covered up, thrown away, either discarded or overwritten, right? But what if we have a visible fragment? So this is an idea that we're looking into a scene through a window, and the window is partially or fully transparent, but either way, it's still got this, the window frame and these transparent panels here. So we see the fragment that is the window, and we see the fragments that are the parts of the scene behind the window. And what we want to do is combine the colors together from what's behind the window and the window, and that's what color gets placed on the window as such in the scene. So it's kind of like the window is a camera itself into the scene behind itself, which could get really, really expensive if we wanted to do that. We can do multiple camera renders in a scene. So we do this kind of thing if you're doing, say, a mirror in a 3D world. So we have the render, and then from the mirror's viewpoint, we have another render in the other direction. And so we go, which way are we looking at the mirror? That's the direction the mirror's camera is looking at. Render that, and then render that into a texture in the scene and stuff. I'm going to talk about more about this stuff later. I shouldn't get into it now. I just get excited about things. All right, so let's talk about transparency. So we're talking about the idea that two fragments are going to color one pixel together. So two fragments are now sharing a pixel rather than one of them getting just thrown away entirely. So this is an interesting thing, and we're going to look at how we actually put this together. So first thing we're going to think about is how do we measure the transparency of a color, in a sense. So we're talking about what did we find at certain texture coordinates, what color is there, or what color have we put on certain vertices. And this is where we get alpha. So we've been using red, green, and blue, and we've been using alpha of 1 for everything so far. But now that we get into transparency, we can use an alpha that is not 1, and that means we have an object that can be seen through in some way or another. So any alpha that's not 1 can be seen through. So 1.0 is opaque, which means you cannot see through it. It blocks everything behind it. And 0.0 would make something invisible so that the object wouldn't be seen at all, and you would just see the stuff that's behind it. And gradations in between mean that it's like transparent glass. I don't have any colored glass near me. I mean, I'm not sure who would. Oh, I do. Okay, I just pulled a piece off one of my Lego kits. It's so dusty. Look how dusty that is. But this is partially transparent. You can see part of my hand through it, but it also colors things as well. So this has probably equal parts red and green, plus some really dirty texture for the amount of dust that's on this. But it is not opaque, so it would have an alpha that's partial. So we would have the colors of the things behind it, as well as its own colors being rendered for that fragment that's in this object. I love the fact that I have Lego kits just sitting around my room like that. I think it makes things very easy. Like, this would be much harder to do if I'm lecturing in person. The odds of me remembering to bring colored glass in person to a lecture is basically 0. Okay, so the alpha component, we've seen it. We've been ignoring it up until now, but now we're gonna start using it. Hexus one's making fun of me for not putting my Lego in a glass cabinet. My miniatures get to be in the glass cabinets because I've painted them, and the Lego is less. It's like a level below the level I want to protect. But anyway, let's look at the simple way of doing this. The simple way is discarding fragments. In the same way that we're discarding fragments for being in front or behind each other, we can have fragments below a certain visibility threshold. So we could set this visibility threshold at alpha 0.01 or something like that, like a very low amount. And what we can do is we can say we can actually discard the fragment in the frag shader. So in the frag shader, we can sample the color at that point. So at that point, we're going to look at the texture. And so this is the full texture here. And the colors here, this is us ignoring the alpha in the colors, and this is us using the alpha in the colors. But in this case, for these tufts of grass, we've just got an alpha 1 for the grass and alpha 0 for the gaps behind the grass. But what we do is actually have a rectangle for each tuft of grass. And the trick is, all we're doing is we're saying that in the gaps between the grass where our alpha is 0, the fragment is discarded. So we don't even have to do anything special with this. This is just a different rule for discarding fragments. So when depth testing, we were discarding fragments based on their depth. Now we're also discarding some fragments based on their alpha value. So if the alpha value is 0, we discard the fragment, which means the fragment is unable to write any information to the frame buffer, which means it will not appear in any way. So it won't obscure other things, and nor will it appear in the background when other things are rendered or anything like that. So this is actually how heaps of stuff is done. And this is also how sprites are done in 2D. You know what I was talking about in that Mario game, that kind of case study that I did of something like Mario? When we had that sprite sheet, the background of that sprite sheet would have been transparent like this, so that when you place Mario in the scene, you wouldn't have had this white border around him. You would have had this gaps around him, in the same way there's gaps around the grass like this. Grass tufts and stuff like that are sometimes modeled with geometry, but they're sometimes modeled just with what we call a billboard, which is just like a rectangle with alpha cut out. So so it just looks like this. Another trick that we do with these, a lot of games you will see these. If you walk around the piece of grass, it rotates to you. So what we actually do is these tufts of grass in most games, well, not most games, but a lot of games, have a rotation matrix on them around the y-axis that is really similar to the camera look at rotation, but instead of it being the camera look at rotation, it's the look at camera rotation. So these things are always looking at the camera. So no matter where you're looking at it, it looks like this luscious tuft of grass that's circular. And if you walk around it, it still looks circular because it's following you around. So you can do cool stuff with these kinds of things. And you get away with it because if you're just running past this thing in a distance, you go, oh, there's grass there. You never get side onto the grass to see that it's flat because it just follows you. Cool little tricks like that. That's not really a graphics trick. That's more of a gameplay trick. But these are the things that remind me of the fact that computer graphics is not about simulation, it's about trickery. If you can trick people into believing something, you've done just as well as if you've done a completely realistic simulation of it, but you may have saved yourself a significant amount of computing power doing it. So anyway, that's a little thing about tufts of grass. But yeah, what we're thinking about here is the transparency. So transparency is reasonably easy if it's either visible or not visible. If it's visible and just covers up everything, that's fine. If it's invisible, it's discarded entirely. Yeah, and as Sam's saying there, to discard a fragment in the fragment shader, it's a keyword. It's literally, you just write the word discard in a semicolon, and the frag shader will stop there and will throw the fragment away. So it's pretty handy. But this might not be the only situation we're going to have. That does make for easy transparency, and you don't have to do any other work for that if you're going to just discard something. It's just a little bit of code in your frag shader. But if we don't have that nice transparency that we could just throw anywhere in our scene, and we have stuff like colored windows, or we have stuff like my Lego kit over there, we have a canopy for a spaceship that's a particular color. So I don't know why it's that color, but sometimes things are colored just because it's cool. Or we've got like shop front windows in a scene that have like a slightly blue sheen to them to make you kind of recognize that there's an inside and outside, that kind of thing. A lot of that stuff is going to require some kind of transparency. So this means that if there are 2 fragments on a pixel, it could be more than 2, but we're just going to look at 2 fragments for a pixel for the moment, and the front one has an alpha that is less than 1. If the alpha is less than 1, it's partially transparent, which means you should be able to see some of the color that's behind. And there's a simple formula for how we might do this. Is not the only formula. There are other options in OpenGL, but a simple thing would be the front color multiplied by their alpha. So, for example, if something is 50% transparent, actually, let's not do 50%. Let's say something's got an alpha of 0.8. You can only just see through it, but it's mostly its own color. So, 0.8 of the alpha means the front color times by 0.8, and the back color times by 1 minus the front's alpha. So, 80% of the front, 20% of the back. So most of it is the color that's on the front, but some of it is partially see-through, partially transparent to see the one behind. And that mixes the two colors together for what gets rendered in that pixel there, which can see both of those objects, gets the color that's mixed between those two fragments. And it's really based on how transparent the front fragment is. So it's a pretty simple idea when you think about that. So you just mix the front and back fragments together in such a way that the amount of transparency in the front fragment defines how much of each of the two colors gets put together. And the nice thing about this as well is that front alpha and 1 minus front alpha adds up to 1. So we're not going to be accidentally multiplying these colors to the point where they go outside of the range, which is something that can happen. We haven't talked about this actually, is that if we have a color value that overloads or underloads the float, then we have some weird issues. We'll talk about that later. But we have that possibility where we just go all the way to the end of the color spectrum and we end up getting clamped there and our colors start to shift into different spectrums by accident. But this, because it's an even amount from each, won't be able to overflow or underflow the floats in the colors. So we can blend, but I don't know if you noticed an ordering issue there. So we're rendering the front fragment, and we need to know what color the back fragment was rendered to be able to do this. Or we could say we're rendering the back one and we need to know the front one, but that's a bit weird. It's hard to know what's going on there. Either way, generally the front fragment needs to have the back fragment already rendered before it can render. So the transparent object needs to know what was rendered in the background. So what happens if the transparent object in the front is rendered before the background? We have no guarantee on the ordering. Remember, we abandoned the idea of ordering. So if we have no information on what's behind the transparent object, then we can't mix them together. We can't just sit there in the fragment shader and wait for the other fragment to get rendered and then return to this code. It's not how the graphics card works. It's just going to go in lockstep and finish all its fragments and move on to the next fragments. So if we have no information on what's behind it, then we can't render the transparent object, which means order is important. So we have a problem here, because I've already spoken today about what the issues are in trying to order all our triangles. But it's not necessarily, this isn't a death knell for transparency, because we've seen transparency in games and stuff like that. You would have seen a little bit of it. Interesting point. There's very little transparency in games. There's a whole lot of places where transparency is possible, but you're very, very unlikely to see houses with like multiple windows where you can see all the way through and stuff like that. A lot of people, when we're developing things for games, we're super, super careful about how much transparency is in it, because it's actually very expensive. But anyway, let's talk about this in a moment. Okay, so what we can do, all non-transparent objects can be rendered first, and then any transparent objects are rendered afterwards. If we're doing it this way, what we're doing is we're guaranteeing that when we render a transparent object, the background's already been drawn, which is a good thing, right? So whatever we're looking at through this window, say I'm looking through a window into a house and there's a chair and a lamp and stuff like that, I can see them because they were rendered first, and then I can blend with the colors in the background and the colors of the glass of the window, right? So that's going to work reasonably well. So what we do is we go, okay, non-transparent objects are just rendered normally. No worries. We just do their normal render path with their Z depth and all that kind of stuff. And then we'd render the transparent objects afterwards. We say, if there's a window that's visible, we already know what's behind it. We mix the colors together, and that's what color that will show through the window. So that totally works, right? This works. Yeah, this works fine. Perfect. No problems here. No problems here. No problems here. If I ever have a slide with this many question marks on it, it means that there's a problem. So, what if there's multiple transparent objects? And those transparent objects can see through them to other transparent objects. Are we going to have a problem here? Yes, we are going to have a problem here, because this one was rendered first. And then this one, if I'm looking at it correctly, this one was rendered next. Its Z depth was behind this one, so it didn't render. And then this one was rendered. So it could see this one because it had been rendered previously, but it couldn't see its Z depth was behind this one. So it just didn't render over the pixels that it was behind in Z depth. So here's an issue where it's not just as simple as saying do all the transparent things after you've done all the non-transparent things, because this worst case scenario is the transparent things can see the other transparent things. So I have now piled up multiple fragments. I've got 3 fragments all in a row, or in this case 1, 2, 3, 4 fragments here for this particular pixel. And so what we need to do is render the one at the back, then blend with the one in front of it, then blend with the one in front of that, then blend with the one in front of that, and then we get our final vision. The downside to this is we need to sort the transparent objects from back to front. So here, if the transparent objects have been sorted from back to front, we can then do them in order. So each transparent object will see the ones behind it first before it starts its rendering, and then it will get the correct color of being able to see through these things. So question I have here. Did we or did we not just go through an entire kind of section of the lecture talking about how bad it is to have to literally do a depth sort on objects before rendering them? Yes, we did. And no, transparency cannot escape that, because now we're in a situation where there's no Z buffer to help us here. What we're ending up with is a situation where if we don't depth sort these things, they're not going to render correctly. There are tricks to do it, but none of them are that easy. There's the idea of doing a 3-dimensional frame buffer. So instead of doing a frame buffer that's flat, you have multiple levels of frame buffer going depth-wise, and then you try to guess where your transparent objects are by putting them into different slices of this frame buffer. And then when you put the frame buffer's color to screen, you go from back to front, and you combine all the colors together and you put it together. So it's possible. And that may be less costly than depth sorting all of your transparent objects. But it's not perfect. There are other ways of doing it, like, what do they call it? Depth independent transparency, I think. It's something like that. I can't remember the exact term for it. But yeah, of all those tricks, none of them are easy, and they all offer a great amount of computational use just to get them going. So this is why transparency is a very rare thing in games. This is why you'll see, especially, like, the further you go back in time, the more you'll see this of windows that are done in this format instead. 100% transparent in parts of it, and then the window frame is the only thing that defines that there might be glass there. Or you'll see things where there is, like, you know, at most 2 or 3 transparent objects in the scene at any given time. So if there's only a few transparent objects in the scene, the odds of them lining up like this are very low, and you'll get away with it. Or your depth sorting for your transparent objects is very cheap, because you have this, like, maximum of half a dozen transparent objects at a time. So you go, yeah, we can depth sort that few objects, that'll be fine. But there's no nice way around this, unfortunately. Hexus one saying even Minecraft has issues with transparency. Definitely. Minecraft, I think, would be at a great danger of having issues with transparency, because if you do multiple glass objects one behind each other, you can do that. Like, if we're designing a scene for a game where someone gets dropped into a world, we can just make sure there's not that much transparency going on. But we can't do that with something like Minecraft, where it's like, no, you build the scene yourself. So if you put too many partially transparent objects in front of each other, you may see what feel like awkward drops in frame rate, because this kind of depth sorting or some other depth-based transparency algorithm is running in the background to make sure these things work. And one of the issues as well is, like, how do you know whether you need to put these tricks in or not? If you put all these tricks in and there's nothing transparent in your scene, then you're again just wasting your graphics resources. So it's a difficult situation to have to deal with. So yeah, it's awkward. Okay, so if we're going to try to do this in OpenGL, we're trying to do this in code. OpenGL can help us out a fair bit with the blending. We can actually enable GL blend, which gives us the default blend function, which is this one, front color times alpha plus back color times 1 minus alpha. But you can change it to other options. So I don't remember many of them, but I know there's different mathematical options for what GL blend can do. What OpenGL can't do. So if we turn on GL blend, then we just get automatic kind of transparency. But what it can't do is it can't stop this situation. OpenGL is not going to reorder the rendering of your objects for you. So if OpenGL is not going to help us with render order, then we're going to have to do that ourselves. So if we're going to have transparent objects, we have to do our draw calls in order. So we do all our draw calls for the objects in the scene that aren't transparent. Then after that, we do the draw calls for the transparent objects. Or we do whatever we're doing with transparency. We're doing something simple, like we take all our transparent objects and we take their Z depths and we sort them based on their Z depth. And we hope that no one has put two transparent objects clipping through each other, because then we can't sort them. And then if we do that, then we can render the scene. I guess Minecraft is in a good position because it's a square grid, a cubic grid world. It's impossible to create two transparent objects that clip through each other. So that's a nice thing. I mean, I say it's impossible, but I don't know. I don't know whether you can do something with like partially transparent weapons or something and end up with that kind of, where was it? Back here, the impossible triangle of which one of these is in front. I mean, even this diagram is incorrect, because this turquoise one should be clipping through the orange one at some point. So yeah, we're going to get these ordering issues where, oh wait, which slide am I on? This slide, yeah. So we're going to have to do this manually. So we would have to, we'd have to find out which objects are transparent, and which means we're going to have to organize our scene in such a way that we go, okay, remember that the glass in the windows is partially transparent. We want it to add some color to the scene. All of those will have to be separated from the draw calls of the other objects and then ordered based on their current Z depth in the world and then rendered. Super awkward, right? Because we've actually already delegated the calculation of the Z depth of the objects to the shaders, you know? So we're doing our depth buffer writing in the fragment shader. The fragment shader cannot change the order of objects being rendered. So we're going to have to like double our workload here. So we're going to have to take our transparent objects, transform them. This is probably happening in the CPU, transform them into our view space, which is super annoying because we're doubling up on the work the graphics card's going to do. But we transform them into our view space, decide which one's in front of the other ones, and go, okay, you need to render first before other things. So again, as I said, transparency is very costly, which is why you see so little of it in games. Yeah, so it can work though. And it can have some cool effects. I actually just thought of a game that has a lot of transparency in one of its tech demos. Maybe, okay, actually we're pretty close to the end of the lecture. I can show you that in a second. In a second I'll show you. But yeah, so let me go back over everything we learned today. So 3D is giving us more capabilities to do things, but it is also starting to make things more complicated. And so what we're looking at today is a lot of techniques dealing with complicated situations. So we are trying to replicate things that we believe should exist. So we believe that if you move an object, all of the things attached to it go with it, right? So we're going to use a scene graph for that. We believe that the character is a single object, but it could be modeled as multiple objects. So we're going to use the scene graph to keep it together in a sense, and also control the transforms between things, make it easy to work with a hierarchy of objects. Depth testing, seeing what is in front of behind things, is not simple. In polygon rendering, it requires some maths to get it going. And blending and transparency are potentially very costly things in terms of like computational power, but what they can give us is the appearance of things being in front and behind each other in an interesting way. So let me hop into. Jason says rip windows and water. Yeah, looking through a window into water. That's like, you can see plenty of games that do that, where something like water or something happens, and what they will do with that is they will often not do transparency. What they'll actually be doing is just rendering the stuff that's through the water and adding a color to it and shifting it. So when you look through water, the beam of light actually turns as it goes between the different density of the water and the air. So what they'll do is they actually take the objects and translate and scale them a bit and color them differently, but there won't actually be a transparent surface on the top of the water being rendered. There's lots of little tricks like that. So let me show you a game that I played recently that had transparency. So that's actually kind of like the lecture's officially kind of over, but then also this is kind of part of it. So let me show you a game that I was playing recently. World War Z. I can't 100% recommend it for gameplay. It's okay. It's pretty good. It's like the Left 4 Dead style games, but its graphics benchmarking test had a scene that was that had a lot of transparency in it, but it'd be interesting to look at how they did that transparency and whether it actually makes sense or not. It's just in the settings, video settings, run benchmark. So I'll just run the benchmark here and you get to see it. Mark Chief forgets the word refract. Yeah. What's that? Next Monday? Something happening next Monday? Oh, hi Jackson. Yes. I'm sorry, I've been hiding from my work. Okay. So check out all the transparency here. Multiple levels. I have no mouse cursor, so I can't show you. Multiple levels of transparency with different colors, but not only different colors, but the shape of what's behind it refracting a little. And we can see the partially broken bits of glass that are a bit darker there. So it's kind of interesting that this is working as well as it is, but I think this is just an idea of using modern hardware for this transparency, and we're getting away with it. The other thing that works really well here that you can see is that all of the transparent objects are on these perpendicular surfaces. So they didn't have any transparent objects on any angles. They're all on flat walls and things, and that way you can definitely tell which one's going to be in front of the others. So they made it really easy for themselves to deal with ordering for transparency like that. Anyway, that's just a little example of it. Okay, that's it for the lecture today. Thank you all for coming along. I hope that this helps get you a little deeper into some of the little tricks and stuff, because like this is like kind of like we've got a lot of the core of what you need to know about like 3D rendering, like polygon rendering and stuff, but there's a lot of these things which are very important to how we're going to be working with this stuff. And like the scene graph allows us to like kind of lower the complexity of building objects and stuff like that. Depth testing is something important because like otherwise things just don't look right. And transparency is like a kind of an optional thing that once you know how hard transparency is to do, a lot of games you play from here on, you will notice how they dodge the transparency issue. Like windows that are just painted blue and you can't actually see through them and stuff like that. Other windows that are 100% transparent where you're like, I think that window shouldn't be, like, should have colored the scene somewhat, you know? And so you'll see people jumping through hoops and pulling off little tricks to try to get transparency to work in their scenes. Okay, I'm gonna wrap it up there. I will go actually just quickly before I wrap it up, does anyone have any questions? Because I feel like I would go and come back for questions, but I feel like there's not going to be that many people here in real time today because this is just like a recording for people to watch later. So if anyone has any questions, fire them off now. Otherwise, I might just wrap it up as it is. Give people a little time because I know there's a delay. Oh, Anthony had one, but you forgot. Don't worry. If you remember it later, pop it on Ed or Discord, depending on, you know, whether it's just a conversational one or whether it's like a really technical thing that you know other people are going to want the answer to. It's still making noise in the background. Karate asks, Karade? I'm not sure. Asks if there are any plans for any guest lectures. I haven't really made plans. I was thinking of something in week 6, but I haven't actually asked anyone yet. So I'll think about it. I was actually thinking about getting a friend of mine who works in the games industry now and used to teach game art to come in week 6 and just talk about things. I'm going to talk about it a bit in week 5, but he might be able to give us another perspective on things. We'll see how we go. I don't know if he's necessarily got time to do that, but yeah. But I haven't otherwise made any plans for the guest lectures or for things in week 6. All right, I'm going to wrap it up there. Thank you all for coming along. Those of you who could make it, obviously it's optional because this isn't our regular time, so heaps of people probably had stuff on at this time. If not, other people are probably watching this as a recording. Hopefully you learned something useful from this about scene graphs, depth testing, and blending. All right, see you all later.